Hello everyone, my name is Yash Patel and this is my lab 3 on finding the unknown mass of a black hole. So for the procedures and goals, the goal of this experiment is to find the unknown mass of a black hole, and we have some initial conditions that we have to work with. So first of all, the mass of the star orbiting the black hole is 2 times 10 to the 30th kilograms, and we also have the position data in x and y coordinates, and we also have a unique trajectory which is generated from my email. The procedure to solve for the mass of the black hole is as follows. So first, we want to calculate the net force acting on the star. We want to do this by using position data to determine the star's position at a given time step. And finally, we want to use Newton's law of universal gravitation to solve for the mass of the black hole. All of these computations will be done on GlowScript, which will make it much easier on us. And on the right, you can see the principles that are used for this model. We use the rate of change of momentum, the parallel component of Fnet, the perpendicular component of Fnet, and finally Newton's law of universal gravitation, which we will ultimately use to solve for the mass of the black hole. This is the GlowScript code for the initial conditions. As you can see, delta T is set to 86,400 seconds, and this is because this is the amount of seconds in one day which we will use for our time step. This is the GlowScript for some of the first calculations. So the first 2 lines is a list that is populated with the x components and y components of velocity, and then the while loop calculates the x component of velocity and y component of velocity using the position data. And this is the GlowScript code for the calculations of momentum and velocity, and also the Fnet and dp/dt in the parallel and perpendicular directions. So you can see that we set Fnet equal to dp/dt and Fnet parallel equal to dp/dt parallel, and finally Fnet perpendicular equal to dp/dt perpendicular, and this is all because of the momentum principle. And one of the most complicated parts of this code is how we calculate the parallel component of net force. So we did this by using the change in the magnitude of momentum over the change in time times the unit vector. And you can see this equation on the right. So this is just a code for how we calculated the net force of the system. So this is the most important part of the code. This is where we actually calculated for the mass of the black hole. So first we calculated the magnitude of the net force. Then we calculated the magnitude of the distance from the black hole to the star, and finally we solved for the black hole's mass by rearranging the universal law of gravitation. We can see this equation on the bottom. So we set the black hole's mass to be equal to the force times the distance squared over the universal gravitation constant times the mass of the star. And this is how we got the unknown mass of the black hole. And this is the code for the visualization, which we will see in the next slide. So this is the visualization. As you can see, as the star gets closer to the black hole, the arrows grow bigger. And this makes sense, right? Because the gravitation depends on how close or how far away the star is to whatever mass that is attracting it, which in this case is the black hole. So I can play the video one more time. The orange arrow represents the total net force, the red arrow represents the net force in the parallel direction, and then the yellow arrow represents the net force in the perpendicular direction. If we can see it one more time. So the mass of the black hole. So on the right, you can see the simulated mass and then the average mass. The simulated mass fluctuated, and this is because of the large time step that we used, which was 86,400 seconds. But we found the average mass of the black hole to be 1.85329 times 10 to the 34th kilogram. And again, this was computing using the following formula, which is the black hole's mass is set to the force times distance squared over the universal gravitation constant times the mass of the star. So what does it mean? How is net force and its parallel and perpendicular components different from the rate of change in momentum and its parallel and perpendicular components? Numerically, they're the same value, which is why we can have the following relationship, Fnet equals dp/dt, but conceptually they are different. We can think of it as a cause and effect relationship where a change in net force causes a change in the rate of momentum. In other words, momentum is what keeps an object moving, while force is what causes this motion. Now, imagine the black hole whose mass we found was removed and a different black hole was placed in the same location. Could you tell the difference? So in other words, is it possible for you to find the value for the mass of the new black hole that is different from the mass you found for the original one? So simply put, this is not possible. This is because we are only using position data and the star's mass to calculate the black hole's mass. We're also assuming that the black hole is the only force that is acting on the star. So as a result, if a new black hole was introduced and the star's trajectory was unchanged, there is no possible way that the mass of the new black hole would be different. And that is the end. I hope this was informative, and thank you so much.